All right, so today I want to be talking about this very special integral. So I'm going to call this as f of n, which is equal to the integral from 0 to pi upon 2 of cosine power n theta d theta. So I want to see if there are any interesting properties of this integral. So let's just see what we can do. So I can write this thing as the integral from 0 to pi upon 2 of cosine power n minus 1 theta cosine theta and d theta. So the basic idea behind this is that maybe I can use integration by parts. I mean, I know I cannot take the integral of this thing, so I could actually take the derivative of that thing, so I'm going to differentiate this thing and I'm going to integrate this thing. Yeah, that will be better. So integrating this thing, you just get sine theta. So sine theta cosine power n minus 1 theta, and this goes from 0 to pi upon 2, and then minus the integral. So it's sine theta, obviously it goes from 0 to pi by 2. And what's the derivative of cosine power n minus 1 theta? Well, it's n minus 1, and then cosine power n minus 2 theta, and then the derivative of the inside function, which is cosine theta. So the derivative of that thing is minus sine theta, so positive sine squared theta, something like that, d theta. Notice that this thing is actually 0, so like ignore that. And this thing is going to be n minus 1, and then I can write this thing as the integral from 0 to pi upon 2 of cosine power n minus 2 theta d theta, and minus the integral from 0 to pi upon 2 cosine power n theta d theta, right? Because I can write sine squared theta as 1 minus cosine squared theta, so I can break this integral into 2. Okay, so notice that this thing is actually the same thing as f of n, so I can replace this by f n. All right, and this is also equal to f of n because that's what we are computing. So from this I can say that n f of n, that should be the same thing as n minus 1 integral from 0 to pi upon 2 cosine power n minus 2 theta d theta, which turns out to be f of n minus 2. So it is the same thing as n minus 1 f n minus 2. All right, so that's gonna give me f n is equals to n minus 1 upon n f n minus 2. But guess what, I can actually write this thing as n minus 1 upon n, and then n minus 3 upon n minus 2, using the property which we just built right now. So like consider n minus 2 instead of n, and n minus 4 instead of n minus 2, and then the same thing, like the same equation stuff. Okay, so f n minus 4, yeah, that should be nice. But then I can also write it as n minus 1 upon n minus 3 upon n minus 2, and then n minus 5 upon n minus 4 f n minus 6, and you can see where this is going. So this can be written as n minus 1 into n minus 3 into n minus 5, and so on. So like it keeps on going upon n into n minus 2 into n minus 4, and so on, right? So where is this going to stop? It will either stop at f sub 2 or at f1, right? So f2 or f1. Well, let's just take two cases. So instead, let's just do it like that. Okay, so now we need to find what f2 and f1 are going to be. Yeah, so let's see. F2 is the integral from 0 to pi upon 2 of, well, cosine squared theta d theta. But guess what? It's also the integral from 0 to pi upon 2 of sine squared theta d theta. Because basically, like, cosine theta and sine theta will take all the values of each other when they go from 0 to pi upon 2, because they are complementary functions. Yeah, so that's really nice, which means I can write 2f2 as the summation from 0 to pi upon 2 of 1 d theta. Well, that's really nice because it's just wait, what? It's kind of weird. Should it stop at cosine squared theta, or what is this thing? So that would be like pi upon 2 radians. Whoa, that's weird. uh Wait, if it's, what about f0? So like cosine power 0 theta. Yeah, I mean, you could also do that thing, so yeah, sure. So cosine squared theta from 0 to pi upon 2, it's like that's gonna be from 1 to 0, something like that. Yeah, cool. This is really weird. I wasn't expecting this to be pi upon 2, but well, whatever. So this is actually pi upon 2. Am I going wrong somewhere? Well, I don't think so. I mean, this reasoning is in fact correct that cosine can be replaced by sine. So that should be correct. In that case, I can indeed write f2 as the integral from 0 to pi upon 2 sine squared theta d theta as well. Right? Yeah, I mean, you got the same values. So it is doable. So in that case, 2f2 should be pi upon 2. That's kind of weird, but okay. So f2 is pi upon 4. Hmm. So looks like that when this thing like stops for f2, that thing is going to be all this stuff into pi upon 4. Okay. But what if this is f1? So like f1, that is the integral from 0 to pi upon 2 of cosine theta d theta, right? Well, what's that going to be? So that is, I think it's going to be well, let's see. So the yes, like the derivative of sine theta is cosine theta, what am I thinking about? So it will be sine theta from 0 to pi upon 2, and that turns out to be 1, right? So f1 is 1 and f2 is, I don't know why, but for some reason it's pi upon 2 something. I mean, that's really weird. I was not expecting that to come out. But alright then, so it's nice. So what do we know? So whenever this will stop at f1, you will get fn is equals to this thing n minus 1 into n minus 3 into n minus 5 and so on. So like, yeah, and then n is supposed to be odd over there. Wait, is that odd? Yeah, it's odd. So all these numbers are even, so like eventually you will get 2 and this upon n into n plus, sorry, not plus, n minus 2 and then n minus 4 and so on. So like even you will eventually get 3 over there, right? And this thing into, well, I think f2 would be, no wait, this would be f3. So like f3 would be 2 by 3 of f1. So like this thing into f1 is just 1. So whenever n is odd, so if n odd, then you're going to get this thing as the value of f of n, and if n even, then f of n is going to be n minus 1 into n minus 3, n minus 5 and so on. So yeah, and n is like even, so these numbers will be odd. Yeah, that makes sense. So like it will eventually stop at 1, correct? And then this is like upon n minus, no, n into n minus 2, n minus 4 and so on. So like 2 into f2, right? It's like f2, wait a second, no, that doesn't make sense, does it? It's like no, if n is even, yeah, if n is even, it should really stop at f2. So well, f4, that thing should be like 3 upon 4 into f2, something like that. And then can I do the same thing with f2? Can I write it as 1 upon 2? Well, I don't think so. I mean, like f2 didn't turn out to be 1 upon 2, right? f2 was the integral from 0 to pi upon 2 of cosine squared theta d theta, which also turns out to the integral from 0 to pi upon 2 of sine squared theta d theta, and then we can add them up, and this is, yeah, it's really weird. I don't know why it is turning out to be like that. I mean, why is this happening? It should be 1 upon 2. In that case, you would get a really nice general value of f of n, but it's not 1 upon 2. It's something completely different. It's like pi upon 4 something. So alright, so like f2, which is pi upon 4. So for even n, it should be this thing into pi upon 4. I know it kind of doesn't make sense that why are we getting irrational and rational terms for odd and for even and odd respectively. It's not wholesome. I mean, you should also get something rational for even, right? Or should we? I don't think so, because this is what maths is telling me, that f2, that should be the integral from 0 to pi upon 2 of cosine squared theta d theta. That should be the integral from 0 to sine squared. Yeah, I mean, like, even if I break it as the integral from 0 to pi upon 4, that would be pretty much the same thing, right? So it would be like, yeah, yeah, that makes sense. So it is indeed pi upon 4. It's not 1 upon 2, is it? No. Yeah, that makes sense. Okay, cool. So that's it. We will stop over here. You know, I really wished that if n was even, this would turn out to be a rational number as well, but it's not. So whatever. We can't do much about it. So yeah, I'm gonna stop over here.